Right, so you can see from my title that I was also trying to break into the observation session of yesterday and the non-Gaussianity, non-linearity session of this afternoon, or at least to say that in all-sky data assimilation, we're already trying to deal with observations that have correlations and have non-Gaussianity, essentially at the moment in a framework that is not supposed to handle those things, but we're trying to do it anyway. So just to overview the talk, there are unfortunately too many slides in this, so I've got two halves. There's a review of observation error modeling as it relates to all-sky data assimilation, and then a section on some new correlated observation error models for all-sky infrared and all-sky microwave that have just been developed over the last year or two. So I'll start with the overview and go quite quickly, and then hopefully have more time to spend on the correlated observation error models. So to give some context, this is about ECMWF medium and long-range forecasts. Over the last 6 years, we've been monitoring the adjoint-based forecast sensitivity to observations, similar to EFSO, only adjoint-based. This is a measure of the impact of all the different observing systems. It's done so that it adds up to 100% over time. And you can see the changing impact and seasonal impact of different observation types. But what we're interested in here is the thick black line, which corresponds to satellite microwave radiances sensitive to water vapor, cloud, and precipitation. And the reason those have got more influential over the last 6 years is down to the advent of all-sky assimilation and adding more observations and doing better over sea ice surfaces and land. So it's not just all-sky, it's a whole series of things that have gone into improving the use of that data. But it's now pretty much the most influential set of observations if you look at it this way. We can look at another line here, the blue line. This is for infrared water vapor radiances. And those actually have quite a similar information content to the microwave radiances that we're assimilating in all skies. But we only as yet use them in clear skies and certain limited overcast situations. And those observations are not having nearly so much impact. It's too simplistic to say that we'll be able to go up to 20% impact by just doing all-sky assimilation, but clearly there must be something to be gained if we can do all-sky assimilation for infrared. So the context of these observation error models I'm presenting is first to get more out of this very influential observation type, which is the all-sky microwave, and also to try and start doing all-sky infrared assimilation. The reason we need correlated errors for that is to be able to deal with hyperspectral instruments, which are already using a correlated observation error matrix. To think about the observations, the observation minus background and the model, is really to think about the errors. And we're looking at the errors in the innovations, the O minus Bs. Where do they come from? They come from background errors, they come from the observations themselves, and they come from representation errors. So the observations here, you can see they've got quite a slightly different structure to the forecast model. So these blue areas are cloud, and you can see that in the observations, the clouds have slightly different shapes, slightly different textures. The model's smoother. I'll point to one little area here which gives an idea of the problem. And this is an area of cloud which in the forecast model appears to have some kind of gravity wave structures in it on a 200-300 kilometer scale. In the observations it doesn't, it's a much smoother situation. And my question there is that information, do we really want to correct the model to what the observations see? It probably doesn't make any sense, and the model may not even be able to ingest that information. And a similar question is, say, in some of these tropical convection regions where you've got convection represented slightly differently, more broadly in the model, in slightly different locations. In global, long and medium range forecasting, are you really trying to correct those small details or not? And for us, it works best to treat those kind of errors as representation error. So not to try and correct the system and to have large observation errors instead. So to have a look at these O minus B plots, sorry, let me just explain one more thing. So we're looking at IASI channel 906. This is a infrared near water vapor sounding channel with a low peaking weighting function and strong sensitivity to cloud. We're not attempting to assimilate this, but it's just a very good example of a very cloud sensitive channel. So moving to the next page, we've also got here channel 3002. This is one of the channels I do want to assimilate. It's an upper tropospheric water vapor sounding channel, which also has sensitivity to cloud, but not as much as that lower peaking channel. Just looking at the O-Bs, you can see that in brightness temperature terms, the errors are smaller, and you can't see it on this plot, but the ratio of cloud errors to water vapor errors is more reasonable. The cloud errors don't dominate so much. But what these figures are for is really to have a think about the properties of these background departures. And I'm being agnostic as to where the errors come from at the moment, observation, background, or representation. But whatever these errors are, you can see they're spatially correlated, they're interchannel correlated, so a low peaking channel and a high peaking channel both see the same cloud, and they both see the same cloud errors. And they also have this property that in the presence of cloud, the errors, whatever they are much bigger than they are in clear skies. And we can quantify that a bit in observation space, that moisture and temperature errors are around the size of 0.1 or 5 Kelvin, whereas cloud errors in observation space can be as large as 100 Kelvin. And that's really the problem that all-sky assimilation is trying to deal with, is these very dynamically varying error scales, error correlations, error variances. Just an idea of what the observations look like. This is just a PDF of global observations, but it's if you took the PDF of your prior in an ensemble, you'd probably see something quite similar. It's fairly non-Gaussian PDF, that the infrequent cloud forms a cold tail, low brightness temperatures, and then there's a main peak of the distribution, which is mainly driven by clear sky observations and variations for this particular channel, variations in upper tropospheric humidity. And because cloud is involved, these brightness temperatures are bounded. The very lowest brightness temperature you can have is 100% overcast cloud at the tropopause, where it's coldest, and that gives you a very firm lower bound on the brightness temperature, and the upper bound is set by the upper tropospheric humidity. So the cloud part of that is a kind of a bounded variable. So traditionally, just moving on, I'm really just jumping through the basics, and then we can go on to the correlated observation error model. Traditionally, people would imagine that observation error statistics were globally constant, homogeneous, isotropic, and for example, Hollingsworth and Lomberg looked at global radiation statistics. I'm really not sure that works, because if you put all of the O-B statistics on one plot, divide by the global standard deviation, you see a PDF that's completely non-Gaussian. And this doesn't matter whether you're looking at all-sky IASI or even radiation temperatures. The same feature is still there. But that's, I think, mainly because we're not looking at the data the right way. It's clear that there is variation in observation errors and background errors, huge variation, and that's what explains this apparently non-Gaussian PDF. It's only non-Gaussian because you're looking at it the wrong way. It's lots of different Gaussian populations put together, some with big variances and some small. Well, sorry, maybe to call them Gaussians, it's a lot of different populations with different variances put together. So our assumption for assimilating all-sky observations is that there is this heteroscedasticity. I should just not put that word into the presentation. Let's just call it situation dependence. But we know that observation errors get bigger, or we propose that observation errors get bigger in cloudy skies and are smaller in clear skies. And if we put this situation-dependent error model in and we normalize the departures by that, we go from something apparently highly non-Gaussian to something that's really quite reasonably Gaussian for the range of normalized departures that we're actually going to assimilate, which is about plus or minus 3. I will show a little bit more on that later. So what else? As I may or may not have already said, we're not yet modeling observation error covariances, the full correlation matrix in all-sky assimilation. We're only doing, we've only got diagonal errors at the moment, but we've known for a long time that the correlations exist between different channels, and I showed you earlier also in space, but we're not even going to start looking at the spatial correlations yet. We're just thinking about interchannel error correlations, and these correlations get much bigger in cloudy situations than in clear skies. These are some results that Niels Bohrmann derived a few years ago using de Rosier. So we really want to be modeling that variation not just in error variances, but also in correlations across the different error populations that we've got. The other reason we would want to model error correlations is that there's been a lot of success already in operational centers with using interchannel error correlation matrices for hyperspectral instruments. And for example, at ECMWF, this added 1% to our forecast scores, and the hyperspectral instruments started really benefiting the system. So hopefully we can do the same for all the other sensors. Let's just think about the source of the errors in the background departures. Traditionally, in clear sky areas, the top line of this table, we're in a situation where instrument noise, say AMSUA instrument noise is around 0.3 Kelvin, 0.2 Kelvin, something like that. That quite often dominates. And the other errors in the system, the observation operator is working pretty flawlessly. Any biases in it are corrected. Mainly the representation error is not big. Arguably, the background error is small. So we're in a situation where the dominant error is something that's nearly globally constant, Gaussian, uncorrelated quite often. So you can get correlations in that, but that's quite an easy situation to deal with. And that's what we've been doing traditionally. If we move on to all-sky assimilation, we're trying to assimilate in cloudy areas where suddenly the instrument noise is irrelevant. So we've lost this sort of reference point of Gaussian noise, and our errors are coming from very different sources. The observation operator is not working so well. We don't know all the microphysical properties of the cloud, so we can't perfectly simulate the radiances. I've been arguing that the error of representation dominates. And arguably the background errors, at least for global assimilation, are relatively small. And all of these things are going to be correlated spatially, interchannel, possibly non-Gaussian, and also very situation dependent or heteroscedastic. Not quite there yet, but and I know I just want to explore this representation error versus background error thing a moment on a kind of representation error spectrum. So on one end, this is the way it's working for us at ECMWF. We're assuming that many of the differences we've seen between observations and model are really representation error. So cloud convection processes that are not predictable over 6 or 12-hour assimilation windows, or errors in the model, as in this case, which seem to put possibly a gravity wave perturbation on top of the real situation. Those are things that we don't want to try and correct in the analysis because they'll then blow up into forecast errors later on. But on the other end, you might really want to correct all of these features and have an analysis that looks as close to the observations as possible. And I think that really just corresponds to the application you're working in. Whether if you're doing a cloud retrieval or nowcasting, you really want to fit the data. If you're doing global forecasting, you want to extract just enough information from the observations to be able to improve your long-range forecast, possibly ignoring the short-range detail. And that might be a spectrum from fitting one observation almost perfectly if you're doing, say, precipitation or cloud retrievals, to trying to fit as many observations as well as possible. I'll just skip over that for interest of time. One last thing is the fact that we're doing var QC. It's worth just pointing out that it may be called QC, but that's really just a change in the shape of the error PDF, and that goes non-Gaussian. So just to quickly step through this, we've got the Gaussian cost function on the left and the Gaussian error model on the right. That's the solid black line. But then you can do var QC with either a Huber norm or the classic top hat plus Gaussian model. And that's what we use for all-sky assimilation. And it's extremely important. It gives for all-sky assimilation, it gives a very big boost in the quality of the assimilation. Without it, we basically can't assimilate the data at ECMWF. So we do already have this non-Gaussian error PDF in the model alongside with a situation-dependent error model. We'll forget about that extra model for the moment, but there are some new ones that have been proposed. So to summarize so far, there is some level of non-Gaussianity being addressed through top hat VAR-QC. Some non-Gaussianity is not non-Gaussianity, it's situation dependence, and we are modeling that. And the thing that we're now trying to do is to go on to correlated situation dependent error modeling. So that's what the next part of the talk is going to be on. So one more caveat to put in before we go to that. In most applications, when we're trying to ascertain what the observation error matrix is, we're using something like Desrosiers or removing an estimate of HBHT. In all-sky assimilation, more or less everybody's been just assuming that the expectation of the background departures can be used as a proxy for the observation error matrix. And that's what's going to happen for the rest of this talk, and it's already an assumption in what I've already shown. And that's equivalent to just saying that representation error is very large, so we might as well forget about the other components, the fact that we're just saying that observation error dominates the background departures. The current observation error model has essentially an error matrix for every observation. I is the observation here, but it has no correlations. And the error variances are varying as a function of cloud amount. And this is how the error model is derived. It's the piecewise linear solid line on the right-hand side. And that piecewise linear is roughly fitted to the bin standard deviations of the first guess departures as a function of cloud amount, this symmetric cloud amount. There's no reason why that has to be a piecewise linear model. You could just store the statistics in every bin and have a lookup table. And the importance of that is if you want to go to error, if you want to flesh out the whole error correlation matrix, one possible way is just to have a lookup table of error covariance matrices. So that's what I've tried for the all-sky microwave images. So if we go to the next page, these are just some examples from this lookup table of error covariance matrices. It's got two dimensions. One is total column water vapor to try and address the fact that error covariances are larger in convection and smaller in large-scale mid-latitude situations. And both as you go down the page here, the amount of cloud gets larger and the error variances and the error correlations get larger. And so depending on the amount of cloud, you just pick one of these error covariance, these interchannel error covariance matrices out of the table and use it. And the results of that are, to cut a long story short, very good. This is applying that correlated error model. So on the right-hand side, that's the impact of going from the existing use of the all-sky microwave images with a diagonal error model to now an interchannel error correlated model. And blue is good. Blue is reduction in forecast error through time windows out to at least 5 days. On the right-hand side, you've got the total impact of the microwave images for regional scores. And again, you can see round about a 1% improvement going to correlated errors. So that's something that seems to be working very well, but I've cut out a long part of the story, which I hope I'll be able to flesh out in the last few minutes, is that it wasn't working well to start with. And two reasons for that. One, it was not initially possible to combine VAR-QC, which earlier I told you was very important to actually getting good results with all-sky. It wasn't initially obvious how to combine VAR-QC and interchannel correlated errors. And secondly, I was just applying the matrix without this truncation, which most people seem to do. So without those, the results are terrible. Only with VAR-QC and with eigenvalue truncation, which I'll explain in a moment, do we get good results. So that gives a chance to jump to the other form of the all-sky situation-dependent error covariance model that I was testing for the all-sky infrared. And it's in this context that I'm going to show you how the VAR-QC is implemented and how also some of these things work. So the top figure is the existing clear sky error correlation matrix as derived by Niels Bohrmann, which gave the 1% improvement to forecast scores. On the bottom are the correlation matrix of first guess departures for all global all-sky departures. So that's an all-sky error correlation matrix. And it's highly correlated because cloud affects all the channels equally. So cloud errors affect these channels equally. And that one globally constant error covariance matrix, not just correlation, but error covariance matrix, is the basis for another all-sky situation-dependent error model. So to understand how this works, we think about the eigenvector decomposition of this error covariance matrix. And you compare those two, now not correlation, but covariance matrices. You look at the eigenvectors, and you compare the all sky and the clear sky. The eigenvectors are almost identical, which is very interesting. The main difference is in the eigenvalues. And this shows a number of different eigenvalues from different covariance matrices I've computed. This is just for these 7 channels, so there are 7 eigenvectors. And the operational clear sky is a solid line. It has this floor retuning, so the eigenvalues don't go lower than about 0.6. This was done with a stated aim of conditioning, but I think it's more important than that, as I'll show you in a moment. But whether you take a global error covariance matrix, so departure error covariance matrix from clear sky observations or for all sky observations, without that eigenvalue floor, they all have very low trailing eigenvalues, and they're all quite similar. So again, the trailing eigenvectors and values of a clear sky error covariance matrix or an all sky error covariance matrix are very similar for this particular application. And actually, where the main difference is in the leading eigenvalues and eigenvectors. And so the colored lines here are all sky error covariance matrices, and the black lines are clear sky error covariance matrices. And there's just a lot more, well, the eigenvalues are much larger, mainly in the leading eigenvector and the second eigenvector partially. So essentially what's happening is that the leading eigenvectors are projecting most of the cloud signal, and that's because the leading eigenvectors are essentially seeing the correlated signal across all the different channels. All of those channels are sensitive to cloud. I'm going to skip that point for now. So again, just to understand what's going on, if you've got a cost function, there's a matrix form, a summation form, and this is for diagonal errors. It's just the sum over the squared normalized departure. If you've got correlated errors and you do an eigenvector decomposition, then you can also write the observation cost function as a summation, but a summation over what we might call eigendepartures, which is the departures projected on the eigenvalues, and the equivalent of an eigendeparture observation error is the square root of the observation error's eigenvalue. So that's useful because it means we can start analyzing the information content we've got in all of the different eigenvectors. And this is an easier way to grasp what we're actually doing when we're using a correlated error matrix. If you can do the same with the gradient. For uncorrelated error, the gradient includes this hi, which is the Jacobian. So for any satellite data, we've got a weighting function or Jacobian. That's quite familiar. That's what hi is here. And it's equivalent when you go to the eigen decomposition is H transpose, so the linearized observation operator transpose times the eigenvectors. And we'll call that an eigen Jacobian. So that's the maths. We can have a look at the pictures. They're a lot easier. On the left, we've got the 7 weighting functions or Jacobians of the 7 channels we're looking at in this work. So they've got temperature sounding capabilities at different levels in the troposphere. You go to the eigenvector representation, these eigen Jacobians are completely different. And this shows you quite clearly what the different eigenvectors are actually sensitive to now. So the leading one, the black one, is sensitive to temperature variations across the troposphere. And then, as you might expect, you've got increasing harmonics of temperature oscillations in the stratosphere, and these are derived from linear combinations of the channels, essentially. So the main point is that main leading eigenvector, which is sensitive to temperature variations across the troposphere, is also projecting most of the cloud signal. So we can use that to our advantage. So here, these are the normalized PDFs of the eigendepartures now. So this is the eigendeparture divided by its eigenvalue. You've still got Gaussian PDFs through all of the trailing eigenvectors. As I said, they're pretty much the same in clear sky and all sky. They seem quite Gaussian. But it's the leading eigenvector that's projecting the cloud signal that's not Gaussian. That's the thin line. And the thick line is what we do if we just do an absolutely standard all-sky error model with situation dependence. But we apply it to the leading eigenvalue rather than the observation error variance. And that gets us a lot more Gaussian. VAR-QC, well, what you do with VAR-QC is you just apply your top hat plus Gaussian error model in the eigen basis and not on normal observation departures. It's actually quite trivial, but it's just it works. So now we've got an error covariance matrix which is globally constant, but the leading eigenvalue is being scaled depending on the presence of cloud. And this allows us to vary the error standard deviations and also the correlations. So just by this one variation, we've got a fully adaptive error covariance matrix. I'm not saying this is any better than just having a lookup table like I showed you for the all-sky microwave, but it's another way of doing it. So I realize I'm out of time, so what to do? Just to say that this raw, just to finish off, this raw matrix wasn't working. 100% is a control system with no IASI water vapor channels. The blue is the impact measured against ATMS channels of using the error covariance matrix. It was making the situation worse in the stratosphere. The diagonal model wasn't, but with the eigenvalue floor, things started working. And to cut a long story short, without the eigenvalue floor, the increments were generating gravity waves. And there's a lot of reasons I think that was where that was coming from. But the basic point is that so far this eigenvalue floor has been argued as a way to improve the conditioning of data assimilation. But I think it's a lot more than that. It's that the trailing eigenvectors are projecting higher order linear combinations of different channels. And that's sensitive to a lot of different things. One is if you've got interchannel biases, tiny little biases between channels can then be massively amplified into a signal that you don't want to get in your data assimilation system. Or secondly, some of these high vertical resolution sensitivities look a lot like gravity waves, and that's probably the biggest candidate for explaining this, that we're just amplifying gravity wave signals that are there in the data if we use this additional information that we can get when we use a correlated error matrix. So just jumping over that, and I'll leave the summary up. So apologies for those extra couple of minutes. So I'm finished.
So thank you, Alan.